This is Bob Capetta from the University of Illinois at Chicago, and this discussion is on partial derivatives, min-max problems. This is the third part of that discussion. So this is what we are currently looking at. We want to find relative maximums and relative minimums of this function. Now, what did we have to do? We had to find critical points, and the critical points required us to take the partial derivatives f sub x and f sub y and set them equal to 0. So we had done that, and we had found the critical points were 0, 0, and 1, 1. So now the question is 0, 0 a min, a max, or neither? Is 1, 1 a min, a max, or neither? Earlier in the semester we had the first derivative test and the second derivative test to classify critical points for a function of one variable. We're going to do something similar to the second derivative test here. Recall, if the second derivative was positive, it was concave up and we had a min. If the second derivative was negative, the graph was concave down and we had a max. But this is a function of two variables, so we are looking at hills and valleys. So we're thinking of bowls and mountains. If the bowl is opening upwards, we're going to have a minimum. If the mountain, right, has the peak on top, if it's opening downwards, we're going to have a maximum. So that's what we want to look at. And we're using a similar idea to the second derivative test, so no surprise we need the second order partials to be able to analyze the critical points. So we've got to find f sub xx, f sub yy, f sub xy, and f sub yx. As I said on the previous discussion, f sub xy and f sub yx are the same. The mixed partials will be the same, although I usually like to compute them both just to sort of check myself to make sure I'm doing it correctly. So here's our function and our first order partials. If I want to get f sub xx, partial derivative with respect to x of f sub x. If I want to get f sub y, partial derivative with respect to y of f sub y. And then the mixed partials, partial with respect to y of this one, partial with respect to x of that one. So where do we go? F sub xx is the partial with respect to x of f sub x, which is the partial with respect to x of this thing, 3x squared minus 3y. The derivative of the sum is the sum of the derivatives. That works for partials as well. So the partial with respect to x of 3x squared minus the partial with respect to x of 3y. Partial with respect to x of 3x squared, we can pull the 3 out because that's behaving like a constant. Partial with respect to x of 3y, well, y is perceived as a constant, 3 is perceived as a constant. The partial with respect to x of that constant is going to give me 0. So I get 3 times 2x minus 0, or 6x. So f sub xx is going to give me 6x. So it'll change depending on which critical point you're at. It's a function of x. Now f sub yy is the partial with respect to y of f sub y. The partial with respect to y of 3y squared minus 3x. So the derivative of the sum, or in this case the derivative of the difference, is the difference of the derivatives. The partial of 3y squared minus the partial with respect to y of 3x. Similarly, I pull the constant out, 3 times 2y, 6y here. The partial with respect to y of 3x, y believes x is a constant, y believes 3 is a constant, so the partial derivative of a constant is going to give me 0. And we can get f sub yy is indeed 6y. But now I need to go ahead and get my mixed partials. So my next discussion is f sub xy. That means you take the partial with respect to x first, f sub x, and then take the partial of y of that. So writing the notation down this way, the partial with respect to y of f sub x is the partial with respect to y of 3x squared minus 3y. Partial with respect to y of 3x squared minus partial with respect to y of negative 3y. This, of course, is a 0 because y perceives x as a constant. And the derivative of negative 3y with respect to y is going to be negative 3, although that's a typo. But it's fixed now. So the partial with respect to y of 3x squared is 0, minus the partial with respect to y of 3y. 0 minus 3 is negative 3. So f sub xy is negative 3. Now I want to go ahead and also do f sub yx, even though I know that f sub xy and f sub yx have to be the same. But let's check that. f sub y x is the partial with respect to x of f sub y, which is the partial with respect to x of f sub y, which was up here 3y squared minus 3x. Partial with respect to x of 3y squared minus partial with respect to x of 3x. These variables don't match. X thinks y is a constant, so the partial with respect to x of 3y squared is 0, minus the partial with respect to x of 3x is negative 3. And just cleaned up that typo again. So what we have here is we have f sub xy and f sub yx are both the same, are both negative 3. Once we have all of the second order partials, we can compute d. D will determine whether what we have is a minimum or a maximum or neither. So what is D? D is fxx times fyy minus fxy squared. Or if you'd like, you could say fxy times fyx, but again, since fyx and fxy are the same, we can just go ahead and write them as a square. So in our case, what did we have? So, going back to the previous slide, fxx was 6x, fyy was 6y. We take 6x times 6y minus fxy squared to go ahead and get our answer. So what will that be? 36xy minus 9. So we have two critical points to work with. 0, 0 is one critical point. 1, 1 is the other critical point. We want to evaluate D at each critical point. So at the point 0, 0, what do we have? D is 36xy minus 9. 36 times 0 times 0 minus 9. 0 minus 9 is negative 9. At the point 1, 1, what do we have? Again, 36xy minus 9. 36 times 1 minus 9. 36 minus 9 is 27. So at the point 0, 0, D is negative. At the point 1, 1, D is positive. That will result in different conclusions for what happens at each point. So what is our classification scheme? Depending on D and depending on fxx. Remember what fxx was? In our problem, fxx was 6x. We know that. And in our problem, we have these two D's. We have D is negative 9 and we have D is 27. Using D and using fxx, we can classify critical points as either mins or maxes or saddle points, or maybe conclude that the test doesn't work. So here we go. Here's our first criterion. If D is positive and fxx is positive, then we have a relative min. And recognize this is very similar to the second derivative test. If the second derivative was positive, we had a min. Notice if fxx is positive, we have a min, but only when D is greater than 0. Second condition, if D is greater than 0 and fxx is less than 0, then the function will achieve a maximum. Notice the same issue. If the second derivative were negative back in the second derivative test, it was concave down, and that gave us a maximum. But there's two other cases for us to deal with. What if D is negative, and what if D is 0? In the case that D is negative, we have what is called a saddle point. So you'll notice this surface that looks like a Pringle potato chip. If you travel along this red line, traveling up the potato chip, you believe you've gotten to the top of the potato chip when you get here. If you travel along the blue line, you believe you've gotten to the bottom of the potato chip when you get there. So it's sort of a min, it's sort of a max, but it depends on your perspective. That's a saddle point, and again, I think that name is certainly indicative of the surface. It appears as if a person could ride that like a saddle. Now, if D is 0, that's also similar to our second derivative test. Recall, with the second derivative test, if D were 0, the test fails. An example would be f of x equals x to the fourth. Second derivative is 0, but there's certainly a min at the origin. There's a min at 0, 0. So if you get a D equals 0, you have to use something else to determine if what you have is a minimum or a maximum. So let's take a look at our example and determine what we have in this situation. So at 0, 0, we had D was negative 9. We recall at 0, 0, d is negative 9. If d is negative 9, we have a saddle point. At 1, 1, what did we have? At 1, 1, we had a d is 27. Now, if d is positive, then we have to check f sub x. We've got to check the second derivative with respect to x to see if what we have is a minimum or a maximum. So doing that, what do we see? fxx was 6x. At the point 1, 1, f sub xx is 6 times 1. 6 times 1 is 6. That makes me think of concave up. That makes me think minimum. So according to this, then, we are going to have a saddle point at 0, 0 and a minimum at 1, 1. But let's take a look at a graph to see if indeed that's the case. So we're going to look at a graph of that surface being x cubed plus y cubed minus 3xy. The x-axis comes out this way, the y-axis comes out this way. We have two critical points. One of them is at 1, 1. 1, 1, let's focus on that point, and at 0, 0 at the origin. We believe 1, 1 should be a minimum, and we believe 0, 0 should be a saddle. So let's take a look at the graph and see if that agrees with our analysis. Difficult to see from this perspective, but this point down here corresponds to 1, 1. Let me go ahead and shift it a little bit. Do we see that? So we can see that minimum value. We can see that lowest value that's happening at 1, 1. Now how do we see whether or not 0, 0 is a saddle? Let me again twist this thing around. Do you see how it's saddle-ish? Okay, from this perspective it would be a maximum. Coming down this way it would be a minimum. So indeed what we have there is a saddle point. So to conclude, for a min-max problem, you've got to identify the first order partials, f sub x and f sub y. Set them both equal to 0. The points that satisfy both equations are going to be critical points. Now that requires you to solve a nonlinear system of equations. That is often a non-trivial exercise. But once you have the critical points, then what do you need to do? You need to look at the second order partials to classify the critical points as a minimum, a maximum, or a saddle point. So once we have the critical points, we've got to go ahead and find these 4 second order partials. And then with those, we use those second order partials to compute D. D determines whether what we have is a minimum, a maximum, or a saddle point. And D is fxx times fyy minus fxy squared. And once we're there, then we look at our chart to see what does that represent. If D is positive and fxx is positive, then we have a relative min at the value. If D is positive and fxx is negative, then we have a relative maximum at that value, at that critical point. If D is negative, regardless of fxx, we have a saddle point. And if D equals 0, the test fails, and we have to use a different sort of strategy to determine whether it's a minimum or a maximum. And that will conclude this lecture on partial derivatives and min-max problems.